you know why you're here. Strong and weak. What is the difference between the two? And what you didn't know is we're also going to be explaining how we're getting this difference. And yeah, remember, you can be downloading this PDF so you can be making your own revision notes as you go through. The link is in the description. Okay, so acid strength. So acid and base strength is down to how much the acid or the base disassociates in the solution. So if it fully disassociates, then you have a strong acid or base, as we can see here. So we're having the full disassociation of hydrochloric acid, which is why, yeah, we've got the arrow, and then you have the full disassociation of sodium hydroxide. And then, yeah, whatever the concentration of your strong acid or base, then that's going to be the same as the concentration of either the hydrogen ion or the hydroxide ion. But if it only disassociates a little bit, then you end up with an equilibrium, and yeah, this is a weak acid or a weak base. So this means, yeah, that pretty much most of the solution is staying, in this case is ethanoic acid, and a very small amount is disassociating to give you, yeah, the hydrogen ion for the weak acid, and yeah, the hydroxide ion if it is, yeah, a weak base. So that's what we're going to go through today. But to give you a heads up, when we look at calculations, so strong acid and base calculations are pretty easy, but weak acid and base calculations are a little bit more involved. So something to look forward to in the future. Okay, so now on to how to know what something is. Is it strong or is it weak? And we can do this just by looking at the formula. Well, we can have a good guess by looking at the formula, and you're also going to be explaining the reasons why. So we're going to start off with acid. So here's just like a generic formula for an acid. So with acids, we need to be thinking about how easy it is for the hydrogen ion to form in solution. And yeah, and this is mainly down to how stable the anion is that it is leaving behind. And we also need to have a big difference in electronegativity between, yeah, the hydrogen and whatever it is bonded to. So we've got hydrochloric acid here as an example that we will have a look at, yeah, followed by sulfuric acid. So yeah, with hydrochloric acid, we're getting the full disassociation. And why this is happening is, yeah, there's a big electronegativity difference between hydrogen and chlorine, so that's a plus point. And the chloride ion that is left behind is very stable, and it's because it's a relatively big atom, so the negative charge can kind of be spread out over the whole ion, so that's what makes it nice and stable. If we look at sulfuric acid, so this is a slightly different example, but the ideas are the same. So yeah, so the hydrogen was bonded over here, so yeah, so the difference in electronegativity between oxygen and hydrogen, again, is pretty big. And then, yeah, the stability of the anion, so the stability of what is left behind, so we've got it drawn out here, is pretty high. So, yeah, the negative ion would kind of form here, but it is spread out over the whole molecule, yeah, due to the resonance structure. So if you can remember the resonance structures back from a previous topic, then this is why it is stable. So the ion isn't just on one atom, but the negative charge, yeah, is spread out across the whole of this here compound ion. Okay, very good. So when we look at the weak acids, so with the weak acids, yeah, the anion is not as stable with the weak acids. So even though the electronegativity, so in this case, yeah, the electronegativity is going to be the same as compared to sulfuric acid, because yeah, it's oxygen and hydrogen, but the stability of the anion is nowhere near as stable compared to the strong acids. And because of that, it's much less likely to form. So with ethanoic acid, yeah, so most of ethanoic acid in solution stays undissociated. A very small amount does dissociate, and then, yeah, the negative charge is forming on our oxygen over here. And this does have it can sort of form a bit of resonance, and that does stabilize the charge a little bit, but it's nowhere near as great as what was going on with the sulfate ion. And then, yeah, also with the weak acids, their level of dissociation, so how much this happens, is different for each acid. And then again, yeah, this is due to how stable the anion is. So we will look at this in more detail later in the topic when we move on to the HL stuff. Okay, so there we go. So that's weak acids. Now let's have a look with the bases. So with bases, the idea of stability is still used, but this time it's how stable the metal ion is, how stable the cation is. So with the group 1 hydroxides, they are all strong bases, and this is because the group 1 metals have a very low electronegativity. So their cations are very stable. And your group 2 is very, very similar, and again, we've got a nice stable cation here. But when we look at the transition metals, their oxides and hydroxides all tend to be weak bases. And this is because the oxygen, so the oxygen in either the form of the oxide ion or in the form of hydroxide, form dative covalent bonds with the metal. So they're donating their electrons to the metal. And this is to stabilize the positive charge on the metal. So when it comes to forming a solution, they tend to not be soluble. So these don't tend to be soluble, and they only show their basic character when they react with acids. But if that's all too much to remember, just remember that group 1 hydroxides are all strong bases, and basically everything else is weak, including my old friend and the much loved and mostly used in examples, ammonia. And this is a great weak base, as it's one of the few examples that is water soluble. Okay, now finally, how can we experimentally determine the difference between strong and weak? Well, we can't use a pH probe, that is for sure, as pH is only ever a measure of hydrogen ion concentration. And if we had a solution, a very concentrated solution of ethanoic acid and a dilute solution of hydrochloric acid, their pHs could very much be the same. So because of this, when comparing strong and weak acids and bases, the concentration has to be the same. For example, 1 mole per decimeter cubed. So the first thing we can do to determine the difference is we can do a little experiment. And here is a lovely image generated by ChatGPT. Asking it more than one time, but this is the best that it could do. So what we're hopefully seeing here is that we've got a strong acid and a weak acid. So we've got hydrochloric acid, ethanoic acid, and then this is the reaction with a reactive metal. So this is them reacting with magnesium, and we need to be comparing the bubbles. So what we should be able to see is with in the strong acid, we're getting lots and lots and lots of bubbles of hydrogen because it is more reactive, whereas with the weak acid, we're getting less bubbles of hydrogen because it is less reactive, as we can hopefully clearly see from this beautiful diagram. Okay, the second one is even easier to do. So the second thing you can do is you can use a conductivity meter. So the conductivity meter, once you've got it all set up and you've twisted the dials to show conductivity, you just stick it in your solution, and then you're just reading out the number here. The bigger the number, the more conductive the solution, and then we would expect a strong acid and strong bases to be better conductors as we have more ions in the solution. So there we go, nice and easy. Okay, so that is everything for today. If you enjoyed the content and would like more IB chemistry videos, then please do like and subscribe. It would really help the channel grow. And as we're telling all of your chemistry buddies. All right, so thank you for watching, and catch you in the next one. Ciao.